First topic we're going to discuss this week is exponential equations, and it's important, first of all, to be able to recognize an exponential equation. An exponential equation must have the variable located in the exponent, not the base. I presented you with 4 different equations here, and let's just make sure you're clear on the distinction. When I look for the location of the variable, in the first equation, I find it located in the exponent. That would make this an exponential equation. In the equation below that one, x is the base. So even though there is an exponent in this equation, it's not an exponential equation. It's what we studied previously, a polynomial equation. In the next equation, we have the variable located in 2 different places, but in each case, it's not in the exponent. So this would also be a polynomial equation, while the one below has x, the variable, in the exponent and would be an exponential equation. Next, we're going to talk about how to solve these exponential equations. All right, in our first example, if I ask you to solve for x in the equation 2 to the x equals 2 to the 4th power, that's ridiculously simple, right? I mean, you can just compare the exponents, and if 2 to some power has to equal 2 to the 4th, clearly we know x has to equal 4. So, in other words, when we notice that the bases are the same, we just set the exponents equal to each other, giving us the answer. On the other side of the line here, I've written a similar equation. But notice this time, I have a base of 2 on the left and a base of 16 on the right. But if you are really good with number sense, you know that 16 is a power of 2, and you could rewrite it that way. I can leave the left side of my equation untouched, and 16 happens to be 2 to the 4th power. And then isn't that the same equation that we have over here? So again, once we have the same base, you can drop the bases and set the exponents equal to solve. Now this does rely on you being able to recognize numbers as powers of other numbers. If you're thinking maybe that's not you, don't worry, we'll get to another strategy in the second half of this video. Now let's look at this example down here. 3 to the x plus 5 power equals 3 to the 7th. First thing you're going to check is, are the bases the same on each side? They are. You will ignore the bases, set the exponents equal to each other. And in this case, you get a very simple equation that you now just need to finish solving for x. To get x by itself, we do the opposite operation of adding 5, which would be to subtract 5. I do that on both sides, and I determine that the correct answer would be x equals 2. And let's take a look at one more example of that. You look at 4, and you look at 16. Is 16 a power of 4, is what you want to ask yourself. You want to go always to the bigger number and try and write it as a power of a smaller number. So is 16 a power of 4? Well, sure, it's 4 squared. I leave the left-hand side the way it was, and now what I've done is taken bases that were different and made them the same. Once they're the same, we can ignore the bases, set the exponents equal to each other, and solve this equation for x. Now this is 3 times x, so the opposite operation would be to do division by 3 on both sides, and that gives us a fractional answer, 2/3. There's no reason that you need to go and get a decimal equivalent of this unless my math lab asks you, so just read very carefully when they say what format to give the answers in. Let's look at this next example. You begin as usual by comparing the bases and noticing they're not the same. Now you would look at the side with the larger base and see if you can write it as a power of the base on the other side of the equation. So in other words, I need to stop and think, is 16 a power of 8? Well, we know 8 to the first is 8. 8 squared is 64. So we've already gotten too large. So this tells us that 16, in fact, is not a power of 8. So what do we do here? Well, it requires even more number sense because what you want to do is think about rewriting both sides of the equation to get them to be a matching base. So going back to the 16, we've already seen previously in this video that 16 can be both a power of 2, in which case it would be written as 2 to the fourth, or it happens to be a power of 4, that is 4 squared. And it's just a coincidence that these are the reverse of each other. 2 to the fourth means 2 times 2 times 2 times 2, which is 16. 4 squared means 16. Now the question is, can I use either a power of 2 or power of 4 to express 8? If I want to think about the 4 being the base, I know 4 to the first is 4, and 4 squared is already 16. I'm not going to be able to rewrite 8 as a power of 4. So instead, I'll consider the other option, which is to rewrite it as a power of 2. This is a possibility. 8 is actually the same as 2 cubed, 2 times 2 times 2. So I am rewriting 8 as 2 cubed, and I bring the original exponent that was on the 8 and put it on my new version of 8. I'm going to do the same thing on the other side. 16 is a power of 2. It's 2 to the fourth. So I replace 16 with 2 to the fourth, and I bring along the original exponent. And so now this is what our equation looks like. We're going to apply the power raised to a power rule for exponents in our next step. There is a rule having to do with exponents that says, if you have, for instance, x to the fifth squared, there's a way to simplify this. X to the fifth squared would technically mean an x to the fifth times an x to the fifth. Each one of those x to the fifths is 5 factors of x. So I've written each one that way. Now when I count up how many x's are total in my expression, I have 10 of them. So the simplified version of x to the fifth squared is actually x to the 10th. And most students just memorize this shortcut. When you have a power raised to another power, you multiply them to get the simplified exponent. That's what we're going to do back over here in my equation. When you have an exponent raised to an exponent, you are supposed to multiply these exponents. Be careful on the left because this would require distributive property since one of our exponents is a binomial. This gives me 2 to the 3 times 4x is 12x. 3 times 1 is 3 power. On the right-hand side, my second exponent is just a monomial. So I can just multiply those two exponents together. 4 times negative 2x is going to be negative 8x. And at this stage, I have now gotten both sides have the same base. I'll now ignore the bases, set the exponents equal, and I have to be able to solve for x in this situation. When you have x's on both sides of the equation, you want to bring them together on one side. And usually we don't like the negative signs, so I would go over to this side and I'd want to add 8x onto that in order to make it positive. And I'm going to line it up with the x term on the left. 12x plus 8x is 20x's. I bring down the plus 3, and on the right, everything cancels, but that doesn't mean you just drop off the equal sign. When you have a negative 8x and a positive 8x, they total the number 0, and it's important to put 0 on that side. Now I would finish my equation solving with 2 more steps. Always clear your addition or subtractions first. So do your opposite operation. And finally, this is 20 times x. The opposite of multiplication is division. There's nothing wrong with getting a fraction answer or even a negative answer in this case. Now, all of this relies on the fact that you've got some basic number sense. You have to be able to rewrite numbers as powers of other numbers. And I am sure there are definitely some of you out there who are thinking, that frightens me. It does turn out that there is a second method for solving these exponential equations, which I'll show you next. Now let's talk about a second method for solving exponential equations. Take a look at this next one. Now, when you're looking at it, you might not have any idea whether it's possible to take the bigger number, 134, and rewrite it as a power of 4 or a power of 2, or maybe it's not even possible. Instead, there's another way that you can solve for x, and that is by taking the log of both sides of your equation. Now remember, we have 2 kinds of logs. We have the common log, which is the symbol log, and we have the natural log, and these are the only 2 that the calculator will be able to help you evaluate. So when you use this technique, you want to use one of the logs that the calculator will help you with. Your textbook recommends always using natural log, except for a certain situation, which we'll see. So I'm going to take the natural log of both sides of my equation. The whole reason for introducing logs is because there's something known as the power rule for logs that says if you have a log and inside of it is an exponential expression, you can bring that exponent down in front of the log, and that will be equivalent. So what that does is it takes the 2x, and ultimately I'm solving for x, and it brings it down out of the exponent. So I would have 2x, and I'm going to keep that in parentheses just to keep it looking neat, times natural log of 4 equals natural log of 134. And now you just have to get x by itself. And at the moment, we have a 2 and natural log of 4 on the same side that are multiplying it. I'm going to get rid of both of those by dividing both sides by 2 natural log of 4. On the left side, I'm just left with x. And on the right side is something that my calculator is completely able to evaluate for me. You just always want to be careful when you put this in the calculator and make sure you're using parentheses around any denominators that have multiple parts. So let me show you that. Again, any scientific calculator can be used here. I just happen to have the graphing calculator emulator. And I've typed in my numerator, I've hit my division key for my fraction, and now in the denominator, I'm going to open up a special set of parentheses to type in 2 times natural log of 4. Close it up, close it up. And my calculator is going to give me many decimal places of accuracy. This is where you're going to pay attention to your directions in my math lab because they're going to tell you how many decimal places to give. I'm going to do 3, I think. So 1.76 and always round, so that would be 7. And the benefit to using logs is, as you can see, I didn't have to worry about writing things as powers of other numbers. This process is always the same. You take the log of both sides, use the power rule to bring that exponent down, and solve. This next example has one little wrinkle in it, and that's the fact that my exponential expression's on the left, and then I have something else sitting next to it. Whenever you have an exponential equation, you want to isolate the exponential expression, meaning I want to make sure I get it all by itself. And that can be achieved pretty quickly by just going ahead and using opposite operations to move the 41 to the other side. Once you've isolated that exponential expression, you're ready to take the log of both sides, using one of the two logs that the calculator can evaluate. Now, again, your textbook recommends natural log for everything except for when you have a base of 10 in your equation. If you have a base of 10, a common log, which is a log with the base of 10, is your better choice, and we'll see why. I'm going to take a log, log, which is again that common log, of the left side, set it equal to log of the right side. The next step is always going to be the same, which is to use that power rule for logs to allow the exponent to come out in front and multiply the log. And here I'm going to pause. To solve for x, I would just divide in my next step. I have a log, and I'm going to write the base of 10 on it, even though if there is no base, it's assumed to be a 10. I have log base 10 of 10. And what's that equal to? Does that simplify to something nice? It turns out it does if you rewrite it as an exponential expression. So this would mean I would take my base of 10, a log is an exponent, so my question mark here, my unknown would be the exponent equals the number inside of the log, which is the argument. Now can you tell what value question mark would have? It's got to be a 1 because 10 to the first power equals 10 would be a true statement. So back over here, when your bases match, when you have that 10 here and a 10 there, this whole thing is just equal to 1. So that makes my equation solving much simpler because x times 1 is just x. And so I know that my answer is whatever the calculator gives me for log of 121. Again, just make sure you use the proper log key when you put it into the calculator. And again, I'll stay with 3 decimal places, making this answer 2.083.